My name is Evan Molony. I'm a senior research engineer with CertainTeed Offsite Solutions. My background is in aerospace engineering and building science. Right now, I primarily work on the development of the ONE Precision Assemblies product, including building science work and some new product development.
My name is Matt Trimble. My role with CertainTeed is principal designer, trained as an architect, but have been working in research and development for most of my career and spend the bulk of my time on ONE Precision Assemblies.
The number one thing that I've learned in my time in the building science field is that water is the greatest threat to buildings. I'm not just talking about liquid water like rain. I'm talking about all forms of water. You can have a building that's slightly under insulated. You can have a building that's a little leaky from an air perspective, and that's not ideal. But it doesn't lead to the kind of catastrophic failures that you see if you don't manage water properly.
We go out of the way to ensure that when we think about the ways that water or vapor or wind-driven rain can enter into the building's thermal envelope, that we're taking extra care to ensure that we manage that well.
I specifically talked about water, but you have to make sure you're managing all four of your major control layers. You have to be managing liquid water, vapor, air, and thermal. Cladding is actually really important for the OPA panels. It's one of the first things that we coordinate with our customers because different cladding types mean different design decisions on the rest of the wall. They can affect everything behind it. We have an optional exterior insulation product. It's about 30 millimeters thick of fiberglass insulation. You move inside of that to our primary weather barrier. We use a product called Vicor NVS. That NVS is a full air barrier that wraps around the house. Inside of that, we have our standard structural OSB sheathing. And then when you move inside of that, we use our structural framing. And then we fill the cavity with a dense pack Optima. So it is a fiberglass product, but it's actually blown in and dense packed to a very high R value. We've had a third-party consultant run thermal calculations on the U factors of our assemblies, and just that R25 fiberglass insulation in a 2x6 cavity is enough insulation to meet code in every climate zone, in every code year. So you don't ever need the exterior insulation with our standard 24 on center panel. It's always optional. The next one would be the membrane. It actually changes its permeability with relative humidity. In the roof panel, we manage both air and vapor at the interior. So we have a sheet of OSB on the interior that limits the movement of vapor from the warm and humid interior to the cold exterior to limit condensation. We tape all of the seams with an air sealing tape. We actually frame our roof panels with I-joists. That has a benefit over traditional 2x lumber framing in that the webs of the I-joists are a lot thinner. 2x roof joists would be 1.5 inches thick. And so that's a pretty big passageway or highway for thermal energy to pass into your assembly. It's called thermal bridging. Whereas an I-joist, the web is just a thin 3/8 inch piece of OSB. It's a much smaller pathway for that thermal bridging and energy loss to occur. On one of our pilot homes, we did a blower door test, which is your standard test for testing the airtightness of a house. And I believe before all of the MEP rough-ins and things like that, we had a 0.26 ACH 50, which is air changes per hour at 50 pascals, which is incredibly tight. Another thing that we do is we install this 2x3 layer on the interior. So inside of everything is a 2x3 MEP layer, we call it. And the whole point of that is so that the customer and their subcontractors can run electrical and other MEP without having to poke holes through our finish system. And then when they do have to poke holes through the wall, we actually try to work with them to coordinate where those go ahead of time so that we can, in the factory, put a PVC conduit through the wall or blocking to create a pathway through the wall so that we keep all of those layers continuous. We simulate the movement of thermal energy and moisture through our wall assemblies, but the best work can't account for things that might pop up in the real world. So we knew it was really important to actually test these things in the real world. In the first two houses that we built, we outfitted both the walls and the roof panels with a network of sensors. We put, I think, about 50 temperature and relative humidity sensors in each one, spread out through the walls and the roofs. We also put a couple of temperature and relative humidity sensors inside the house. We also put other sensors in the house. So we put energy current transducers in the breaker panels so that we can measure how much energy all of the electric circuits are using. So we know how efficient are these houses really. We put air quality sensors like CO2 sensors and particulate sensors inside to see how is the interior air quality, how's the ventilation working. And so once you have all of those pieces, you can actually plug those back into our simulation tool to show that the real world data matches what you would expect given our simulations.
In terms of comparison between traditional assembly and our process, one of the big things is the basic difference between a linear process and parallel process. So if you imagine on-site construction, you have to prepare the foundation, you have to set up molds for any concrete that you're pouring, you've got to pour that concrete, it's got to cure, and then you can start to erect your framing onto that foundation. Well, while all of that work is being done on the job site, we can actually be in the factory building panels. And so we can parallel process the house, thereby shortening the speed of delivery. One of sort of the selling points between panelized versus modular prefabricated construction is we can ship panels flat packed and therefore deliver quite a bit more of the building envelope in one shipment. The goal for us as a company isn't just to deliver beautiful houses that are really high quality and that can be delivered in a fraction of the speed of normal on-site construction, but it's also the delivery of this system at a mass scale. When you scale that across hundreds or thousands of houses where we can shorten the time frame based on this delivery method, then it has a real impact.